Welcome to lesson 7.6, 7, and 8. Today we're going to talk about quantum numbers. There are 4 different quantum numbers when we are looking at electrons contained within an orbital. There's the principal quantum number, something called the angular momentum quantum number, the magnetic quantum number, and the spin quantum number. And each electron in an atom has a distinct set of these 4 quantum numbers. So first, the principal quantum number. Principal quantum number n has integral values starting at 1 and continuing to infinity. Principal quantum number n is the size and energy of an orbital. As n increases, the orbital becomes larger, the electron spends more time away from the nucleus, the energy increases since the electron is less tightly bound to the nucleus, and the energy is less negative. The second quantum number, the angular momentum quantum number, has integral values from 0 to n minus 1 for each value of n. So if n equals 2, then the angular momentum quantum number can be 0 or 1. It can't be any greater than that. The angular momentum quantum number is related to the shape of the orbital. For each value of L is given a letter. So if L equals 0, then we have an S orbital. If L equals 1, we have a P orbital. If L equals 2, we have a D orbital. And if L equals 3, we have an F, and then so on. After that, we go alphabetically. Each set of orbitals with a given value of L is designated by giving the value of N and the letter for L. So for instance, you might have a 2s orbital. A 2s orbital means N is 2 and S is 0. All right, let's scroll down here. The third quantum number is m sub L. M sub L can be anything between L and negative L. So if L equals 2, then m sub L, sorry about that, can be 2, 1, 0, negative 1, or negative 2. Values related to the orientation. So if L equals 2, we're talking about a d orbital, and all of these represent different orientations in space. So practice problem number 1 says for principal quantum level n equals 5, determine the number of allowed subshells or different values of L and give the designation of each. So if n equals 5, then L can go from 0 to n minus 1. So L can be 0, 1, 2, 3, or 4. 0 would be an S, 1 would be a P, 2 a D, and so on. Practice problem number 2. What are the possible values for the quantum numbers n, L, and m sub L? This does not indicate a negative here, but n is any whole number integer, 1, 2, 3. L can be 0 to n minus 1. And so this basically practice problems 1 and 2 are just a repeat of the notes we've already talked about. Concept check number 1. How many electrons can be described by the quantum number n equals 3, L equals 3, and m sub L equals 1? So if this is the set of quantum numbers, there are no electrons that can be designated or described by those quantum numbers because L cannot equal 3 if n equals 3. L can only be 2, 1, or 0. All right, moving along. Orbitals. So what do orbitals look like? S orbitals are characterized by spherical shape. As n value gets larger, you get farther away. And those s orbitals have nodes. Those nodes will be where you will not find an electron. So the electron density is 0 there. P orbitals have 2 lobes separated by a node. And so you can see by the probability distribution, and then they can be oriented in the X, Y, or Z direction, because you remember if P is 1, so if L equals 1, then that's a P, so that means M sub L can be 1, 0, or negative 1, which means you can have 3 different orientations because you have 3 different values of M sub L. D orbitals, D is when L equals 2, So 2, 1, 0, -1, -2, 5 different orientations of orbitals. You don't see d orbitals until you get to n equals 3 because you can't have an L value of 2 until that time. And then f orbitals occur when n equals 4. Degenerate orbitals. Degenerate orbitals means all orbitals with the same value of n have the same energy. So basically, these are the same energy and these are the same energy because they have the same value in. Now they're going to differ just slightly, but they're still considered degenerate orbitals, especially the D's and the P's. So electrons within that, any of those 5 boxes or any of those 5 lines will have the same energies. A ground state electron in a hydrogen atom is given just enough energy to get it to n equals 2. Look at the diagram to the right. Which orbital will the electron occupy? So if it's given just enough energy to get to n equals 2, it could be in the 2s, the 2px, the 2py, or the 2pz because they're degenerate orbitals. And then the last quantum number is m sub s, and m sub s deals with the Pauli exclusion principle because it says in a given atom, no 2 electrons can have the exact same set of 4 quantum numbers. And so since an orbital can hold 2 electrons, then they must have opposite spins. So for example, if I have an electron where n equals 1, that means L has to equal 0. That means m sub L has to equal 0. Then I have to have, because that orbital can hold 2 electrons, those are my 2 possible electron addresses. Okay. All right, so let's look at practice problem number 3. Which of the following combinations of quantum numbers is not allowed? You'll notice that the first one is highlighted because the first one, in order for L to be 1, N has to be at least 2. Okay. All right, well, that concludes lesson 7.6, 7, and 8, and we'll continue with quantum numbers in the next lesson.